All right, welcome back to the DP Chemistry curriculum. We're doing lesson 16, 1.4.4 of structure. Today, we're going to be talking about the empirical formula and how it is the simplest ratio of atoms in each element presented in that compound. We will also cover the molecular formula, which is the actual number of atoms of each element in a molecule. Furthermore, we're going to be able to interconvert the percentage composition by mass and the empirical formula. We'll talk about what that means in a moment, as well as be able to determine the molecular formula of a compound given its empirical formula and molar mass. So without further ado, let's begin. And we have to start with a little bit of chemical laws, specifically the law of definite proportions. So you don't really need to have this law memorized word for word, but it's basically the idea that all compounds are made of elements in fixed ratios. Quite simply, what that means is like if we have water, water is always H2O, two hydrogens to one oxygen. Water is not H3O. It is not H2O2. It is not HO. None of those are water. Water will always and forever be two hydrogens to one oxygen. Even more specifically, water is not H2O4. Well, that still has the same proportion of 2 to 1, or sorry, whoops, mix that one up. Uh, Sorry, water is not also H4O2. Well, it's still the same proportion. This is also not water because water is in this fixed ratio of set elements. Um, so water will always be H2O. All right. So with that idea in mind, let's actually look at water specifically. So H2O, one, like we said, has two hydrogens and one oxygen. And what we can do is we can start looking at compounds by mass percent. We can look at compounds by mass percent. So what I mean by mass percent is the percent of each element's total mass. So if we look at H2O, it has a relative molecular mass of 18.02. That is the sum of two hydrogens and one oxygen. Furthermore, its molar mass, which will just dictate as big M of H2O, if you were here last lesson, is 18.02 grams per mole. We can also do the molar mass of hydrogen, which is 1.01 grams per mole, and the molar mass of oxygen, which is 16.00 grams per mole. I mentioned previously that we're going to look at mass percent. So we're going to go ahead and do that. We're going to find the percent of hydrogen by mass in water and the percent of oxygen by mass in water. We can do this. So we'll do percent hydrogen first. Hydrogen has 1.01 plus 1.01 because we have two hydrogens. We'll divide that by our total mass, 18.02, and we'll multiply by 100 to get a percent. This tells us that hydrogen makes up 11.21% by mass of water. 4% oxygen, we're going to do something similar. We're going to do 16.00 divided by 18.02 times 100 to get a percent of 88.79%. That's hydrogen and that's oxygen. So water will always have this percent and it will always have a total molecular mass of 18.02. Those two qualities will always define water. Furthermore, with this, we can work backwards to determine chemical formulas given these ideas. So we can find formulas for compounds given mass information. A real quick sidebar, you might ask yourself, well, who cares about mass information to find formulas? What does that actually help? Well, it turns out we can use something called mass spectrometry or mass spec, which we talked about, to determine, whoops, determine percent mass of each element, percent, whoops, just fully missing this, mass of each element in an unknown sample. What that means is we can get an unknown sample of any element or any compound or anything, and we can figure out the percent mass of each element. And so we can use these to then find out chemical formulas to figure out what a sample is made of. So anyways, going back to working backwards. The best way to do this is with an example, but right before we do, let's talk about the two types of formulas. The first being the title of this, which is empirical formulas. Empirical formulas are quite simple. They are just the simplest ratio of atoms in a compound. Empirical formulas can be the same for different substances, can be the same for different substances. And I'll give you an example. So we have something called hydroxide, which is OH, specifically OH minus. Hydroxide is what makes something basic generally. When we think of a base, we think of hydroxide. It has the empirical formula of one hydrogen to one oxygen. Hydrogen peroxide, which you may think of as something you put on cuts or may think of something as a disinfectant for not stuff you're going to use, like maybe, or sorry, not your own skin, but like metal or something, also has the same ratio of 2 to 2, which is still one hydrogen to one oxygen. These have the same empirical formula, which is simply HO. But they are two completely different things that serve different purposes for us. So that's where we have the second type of formula, which is a molecular formula. A molecular formula is the actual amount of each atom of an element in a compound. So your molecular formula is going to be different than your empirical formula or possibly the same, but molecular formulas will be different for every substance. All right. So going back to what I said from before, we're going to once again use mass percentages to find an empirical formula. So we'll do that with an example. So let's start off with the example that we have a sample of 39.3% mass sodium, Na. We also have 60.7% mass chlorine. So using this, we have to find the empirical formula for sodium chloride. So the best thing to do is we need to first start with a mass, and the best mass to start with is 100 grams. We are going to assume 100 grams quite simply because it's easy to get a mass from percents. If we have 100 grams and we know that we have 39.3 grams sodium and we know we have 60.7 grams chlorine. Furthermore, once we have this, we have to figure out, well, what is a actual chemical formula represent? A chemical formula, in this case empirical, shows ratios of atoms. Now, the problem is I know that sodium, via my periodic table, has a mass of 22.99 grams per mole. And I know chlorine has mass of 35.45 grams per mole. And this is, of course, a molar mass, which means if I have a 1-to-1 ratio of sodium and chlorine, I have 1 mole of each, the masses will not be the same. So unfortunately, if we're using ratios, we need moles, as they will be equal in quantity. While mass will not be equal in quantity, we cannot compare masses because things weigh different amounts. So what I have to do is convert my grams to moles. So I'm going to quite simply do that the way I did when we were talking about molar masses in the previous lesson. So I want moles of each of these, and I need to get rid of my grams. So I'm going to use this handy dandy molar mass. Now I notice the number goes with grams, so I'm going to divide by 22.99 here, and I'm going to divide by 35.45 here. Put a 1 on the top. My grams will cancel. And I will find that within my compound, within my 100 grams, I have about 1.71 mole of sodium, and I also have about 1.71 mole of chlorine. What I notice is these two mole values are the same, which means they come in a 1-to-1 ratio. Therefore, my empirical formula is Na1 to Cl1. And scientists are lazy. We don't like to write subscripts of 1, so we just rewrite that as NaCl. So sodium chloride or table salt has the ratio of 1 sodium to 1 chlorine, and we have found that out by doing math of the percent mass found in a sample. So it's quite a bit. So what we should do is try it again just to get that stuck in our brains. So we're going to try with a different example. You can go ahead and try this example yourself before I reveal the answer, but I'll give you the problem. We're going to start with a sample of 25.94% nitrogen and 74.06% oxygen. So go ahead and try and find the empirical formula between nitrogen and oxygen. And if you can do that yourself, pause the video now and get started. Otherwise, I'm going to go straight to the answer, or I'm going to start going through the work. So, number one, I'm going to assume 100 grams. And by assuming 100 grams, well, 25.94% of 100 is 25.94 grams nitrogen and 74.06 grams oxygen. As I look at those numbers, I realize I need to convert to moles so I can actually compare ratios, or use ratios, So I'm going to go ahead and start the conversion with 25.94 grams nitrogen. I want to lose my grams and get moles. I know from my periodic table, it's 14.01 grams per mole. And that gives me an answer of 1.8, whoops, that's a 5, 1.851 mole nitrogen. Doing the same for oxygen, I have 74.06 grams oxygen. And I want moles, so I'm going to cancel my grams. That is 16.00 grams per mole, once again, the molar mass of oxygen, giving us 4.629 mole of oxygen. Unlike our previous one, this ratio is a little bit harder to compare, but I'm going to do my best. So I'm going to do 1.851 to 4.629. Now, generally, when you have a ratio that is hard to do, there's a simple way to do it. I'll show you with a simple one. If I have a ratio of 3 to 9, I can divide by my lower number, and that would become 1 to 3. So I'm going to apply that same principle over here. I'm going to divide by my lower number, 1.851, divide by 1.851, and I get 1 to approximately 2.5. This is a ratio that I can actually deal with because I know that 1 and 2.5 can both be whole numbers with a simple multiplication trick, which is just doubling both. 1 is already a whole number, but that's all right. So that becomes 2, and this becomes 5. So my ratio is 2 nitrogens to 5 oxygens, and my empirical formula becomes N2O5. Now, really quickly, you might ask, well, why can't we do N1O 2.5? Well, the issue here is you can't have half an atom. You just can't have 2.5 oxygens. That doesn't exist. If the oxygen is split, it is no longer oxygen. Half an oxygen is 4 protons as opposed to oxygen's 8, which is instead beryllium. So we cannot have half an atom. Therefore, our empirical formula is N2O5. So that's empirical formulas. But how do we get to molecular formulas? Molecular formulas, we need extra info. We need extra info. Let's say we take our empirical formula, N2O5. We have the same thing, and we say that this is empirical. But instead of having a mass of a given value, we say that we know the mass of our sample via the same mass spec that we use to figure out the percentages is, so mass of sample is 216 grams per mole. So what we have to do is figure out how do we make 216 be represented by N2O5? Well, the first step is find MR of empirical, which is quite easy to do. I just add the individual ones, 1401 times 2, that's nitrogen, plus 16.00 times 5, that's oxygen, and I get an empirical mass of 108.02 grams per mole. Now, this is a molar mass, so I realize I should not be doing M sub R. I should just be doing M. Uh, but with that said, I still need to get to 216. Well, this is a ratio. We must maintain that ratio. So the way we maintain a 2 to 5 ratio is just by multiplying this by whole numbers. So we can multiply by some whole number to get 216, and I recognize that number is 2. The other way to do it is take 216, divide by 108.02, and you get approximately 2. Therefore, my actual molecular formula is N4O10. So this is how we get molecular formulas from empirical, as we can only get empirical from our percent mass. So I hope this helped and have a great day.